Okay, in question 2, we're given this differential equation, it's second order, and in fact you recognise this is the kind that you can do using a complementary function particular integral, and that indeed is going to happen, but it's not going to happen till part B. That's when they ask us to solve it. Now in an exam, if that's more familiar, you can get straight into part B, leave space for part A, and cash in for, this should be 7 easy marks. But I'm going to do it in order. Okay, you don't have to in the exam. But I'm going to start with the first bit. Now, the first bit is not hard, but it doesn't come up every time. You need to be familiar with the idea of using your differential equation to set up, for a Maclaurin expansion. We're doing an expansion. We're getting triple derivative of naught equals something, and we're getting the fourth derivative at naught. So we've got the first derivative at naught, and the actual value of f of naught, and I've got a differential equation. So the way we do these is we substitute the given values into the equation, and the first time we do that, okay, taking this y here to be naught, so this is the f of x bit, and this dy by dx is the f dashed bit, and we're taking that to be 1. And when we substitute in, we're obviously taking x to be naught, because we're interested in all of these things when x is naught, and we're going to find d2y by dx squared, and that's going to be our f double dashed. So writing that out properly, here's the key information from the question. We're taking x to equal naught in this equation, so on the right hand side we're going to get naught plus 5. Okay, this is our d2y by dx squared when x is naught. And then 5 times dy by dx when x is naught is going to be 5 times my f dashed of naught. So that's 5 times 1. And my 6 times y is going to be 6 times my naught. So I've got a 5 here and a 5 here, and everything else is 0. So this is telling me that f double dashed of x is going to equal 0. Okay. Now I've got to carry on. What have I got to do next in the question? I've got to find f treble dashed of naught. So I've got f double dashed of naught. How am I going to get f treble dashed of naught? Well, if I differentiate the equation through again, this is the trick. If we differentiate the equation one more time, then every derivative moves up one. So this is going to be d3y by dx cubed plus 5 times differentiate dy by dx, we get d2y by dx squared. Differentiate the 6y term, we get 6 dy by dx. Okay, equals, differentiate this, so the 5 disappears and we get 3x squared differentiates to 6x. So, at x equals 0, again, same as before. This time this is one I don't know, so f triple dashed of 0 is going to be what this gives me, plus 5 times d2y by dx squared, well that's f double dashed of 0, so that's 0, plus 6 times dy by dx is my f dashed of 0, so that's 1, okay, excuse me, plus, there isn't anything else, so that's all 3 terms, so there aren't any y's in this one, equals 6 times x, which is 6 times 0, so this is a 0, this is a 0, f triple dashed of 0, therefore, triple dashed of 0 equals, just take this 6 away, so that's minus 6. Okay, is that what the question told me it was going to equal? Yes, it is, so that's good. Okay, we double underline it anyway, even though it's a show that. Alright, so we've got to move on, we've got to find f, the fourth derivative at 0. And this is just rinse and repeat. We're just going to differentiate the equation through again to get d4y by dx to the 4 plus 5 d3y by dx cubed plus 6 d2y by dx squared equals, differentiate the 6x again, and we're going to get 6. And we're going to sub in, this is one we want to find out, this is f 4 dashes of 0. Plus 5 times the third derivative at 0, which is minus 6, and 6 times the second derivative, and the second derivative was 0, and this equals 6, so this is 0, this is minus 30, so f 4 dashed of 0, fourth derivative, of f of x at naught is going to equal 30 plus 6 is 36. Double underline it. Okay, is that everything I had to do in that first part of the question? Yes, I found the value of f for derivatives of naught. Hence, find the first three non-zero terms in the expansion extending powers of x of f of x. Okay, right, well, I've gone all the way up to the fourth derivative, but we've had some zeros, so I think I've gone just far enough for this. So this is just quoting your Maclaurin formula and putting in the values that we've already worked out. So this is just a summary of the things we've worked out. We know an awful lot about the derivatives of this function at 0. Here's the Maclaurin series formula from page 5 of the formula book. So we're going to have f of naught is 0. X times f dashed of naught equals plus 1x, that's x. X squared over 2 f double dashed of 0, well f double dashed of 0 is 0, so the next term is 0 x squared, plus the next term will have x cubed over 3 factorial, and that's times f, it's going to be f treble dashed of naught, so that's the minus 6. And the last, well, the next term will be x to the power of 4 over 4 factorial, and that will be times f4 dashes of naught, which is times 36. Now, I've got a 0 term here, and I've got a 0 term here, but I've now got 1, 2, 3 non-zero terms, which is what I was asked for, so I can just put plus dot dot dot, that's as far as I need to go, and all I need to do to complete this part of the question is to just simplify. So I'm going to get f of x equals, first term is x, okay, 3 factorial is 6, so minus 6 divided by 6 is just minus x squared, and then 4 factorial is 24, so 36 over 24 is actually 3 over 2 x to the power, sorry, this was x cubed, that last one, and this is x to the power of 4. Okay, plus dot dot dot, double underline my answer, and that's the end of part A of this question. And part B of the question, which is completely separate, would have been a re-entry point if you'd got stuck on A. Part B is the complementary function particular integral method applied to this differential equation. So here is the equation, and the first thing we do for the complementary function, we need to set up the auxiliary equation, which is the quadratic. You like to use k, don't you? So k squared plus 5k plus 6 equals naught. For the complementary function, we're solving, we're finding the general solution of the case where that left-hand side equals naught, and we're saving the right-hand side for the particular integral. So the auxiliary equation is the associated quadratic, and you solve that, and your calculator tells you the answer to this. It factorizes as k plus 2, k plus 3. So k equals minus 2 or minus 3. So my complementary function, y equals, you know that you use these, I've got no imaginary or complex roots, so y equals a times e to the minus 2x plus b times e to the minus 3x. We just slot these minus 2 and minus 3 in front of our x's in our powers of e. Okay, that was easy. Now let's do the particular integral. So for my particular integral, I need a trial solution. So I look at what I've got here. I've got a quadratic. So that quadratic, a quadratic trial solution is what I need, because this would be quadratic, this will be linear, this will be just a constant. When I add a quadratic to linear to constant, I'm going to get a quadratic. You know that when you've got a quadratic here, your trial solution is y equals ax squared plus bx plus c. And what we do with our trial solution is we differentiate it. Dy by dx equals 2ax plus b, and again d2y by dx squared equals 2a, and we substitute all of those things into the differential equation, which is going to give us that d2y by dx squared, 2a plus 5 times this one, 2ax plus b, plus 6 times the top one, ax squared plus bx plus c. that all adds up to, right hand side is 3x squared plus 5. And then we're just going to compare coefficients. And if we start with the x squareds, we've got 6ax squared must agree with 3x squared, so a is a half. And then we go on to our x coefficients, so we've got 10a times x here, and we've got 6 times b x, so 10a plus 6b. Coefficients of x have to equal, no x is here, so that equals 0. So 5 plus 6b, 5 plus 6b equals 0. So b equals minus 5 divided by 6, minus 5/6. And then finally, substituting in to find c, we're going to need the constants. So 2a plus, from this we're going to get 5b plus 6c equals 5. And when I substitute in my values of a, b, and c, 2a is 1, 5b is minus 25 over 6, okay, and I can just rearrange that. So 6c is going to be 5 minus 1 plus 25 over 6. Lob that in my calculator, divide it by 6, and you get c equals 49 over 36. So we're pretty much done, except we now need to put everything together. So my particular integral, I now know is a half x squared plus minus 5/6x plus 49 over 36. I need to get my general solution. I need to do my complementary function plus my particular integral. So my complementary function was a e to the minus 2x plus b e to the minus 3x, and I need to add on my particular integral of a half x squared minus 5/6 of x plus 49 over 36, and that was routine. So that was 7 marks for just proving that you know how to operate that general procedure.